So today we're going to start, we're going to talk about, wait, is this today?
Thursday, December 3rd, yes.
This is not, this is the wrong class. Oh my gosh.
Wow, what an insult. Do you think we're in physics 1?
Oh, I forgot to edit this. Oh, dang it. Oh, jeez. This is all your fault, Timothy.
You're not here. If you're here, it'd be different.
Oh my gosh. Do I know how to use computers?
I don't know, you told me.
There we go. Okay. Sorry about that.
I'll forgive you this time.
Thanks. I appreciate it.
Next time.
And I'll turn a blind eye to you eating in my classroom. So we're going to introduce rotational kinetic energy and energy conservation with rotating objects. You can start the new quest assignment. If you're at home, you have to get attendance. If we don't get to angular momentum today, and we probably won't, so we'll do that tomorrow. We'll hold off on the questions involving that concept until we get to that, which will be tomorrow if we don't get there today. They are the questions towards the end of the assignment. This assignment will be a major grade. There will be no formal test over this unit because I'm concerned about not having enough time to do an E&M, and so I'm trying to save a day here and there. So yeah. So the quest assignment is a little more lengthy, and it will be counted as a major grade. Okay. Cool beans. All right. That's all we need this for. Lukewarm. Okay, so today what I want to do, I want to start by proving something that I told you yesterday and showed you, and I don't remember if I did this in AP Physics 1, but just to show you why. Remember when we did the whole rolling without slipping here thing yesterday? We said that the velocity of the, and I'll even call it the velocity of the center of mass of the object as it was rolling. If it's rolling without slipping, then the velocity of the center of mass is the same as the linear speed of a point on the rim of the rotating object, if it's rolling without slipping. That was the condition required. And after class yesterday, I was like, is that on the board? Yeah. Oh yeah. This was the condition. So the velocity of the center of mass is equal to the radius of the actual rolling object times the object's angular velocity. And just to show you that, just to show you why that is, why the velocity of the center of mass is the same as the velocity of this guy, because it's really this guy here that's equal to r omega, right? It's really this guy. But if I can prove that the velocity of the center of mass, or just the velocity of the translational velocity of the object is the same, then I can make this claim here, and then we can solve that problem that we solved yesterday. So how do I demonstrate that? Some people it's obvious to, some people it's not. And so I've marked a little blue mark on the edge of this disc here, and I'm going to wrap up this cord around it. And then I'm going to let it roll, in quotes, I'm going to let it roll down the ramp, and it's going to unroll this rope as it moves down. So at this point, can we all agree that the center of mass of the object translationally moved from this blue mark to this mark, from where it started to where it ended? Yeah. So doesn't this point on the edge have to have gone the same distance, since it unrolled that exact amount, that exact length of rope? Can you guys see that? So that means the linear speed of a point on the edge of the rotating object is going to have the same speed as the speed of the center of the object, or just this translational velocity of the object. Okay. And if that's the case, then we can say, and that's only, if it's slipping, that's not true. Right? If it's sliding while it's rolling, that's not true. That's only true if it's rolling without slipping. And so that's why this condition was required to do that solution yesterday. I thought about that as you guys left, and so I don't even remember, because that's something I definitely emphasized in the rotation unit in AP Physics 1, but That was years ago at this point, and that was when COVID started, so. I bet Timothy remembers that, but you guys probably don't. Okay. What's that? You don't remember COVID starting? All right, so that out of the way. Let's talk about roller coasters. Yeah, exactly. All right, so I got a roller coaster here. It's not a real one. And we've seen this before. You know, I drop the marble and it goes through the loop, right? Now, I did this yesterday because I thought we might have gotten to this yesterday, but we didn't. And so I made some measurements. And remember, we did this or we can solve this kind of problem when we do energy. We can say, and if I have something like this, and we just have an object sliding down, and we want it to get through the loop, we just do conservation of energy, right? We say that the potential energy here, really I can say that the total mechanical energy before is the total mechanical energy after, where for our purposes, mechanical energy is kinetic and potential. So if I let this guy go from rest, it's just initial potential energy, UG naught. But here, he's going to have potential energy and kinetic energy, right? And then we can expand kinetic energy out into 1/2 mv squared, and then do some circular motion stuff to see what the minimum speed is to get through the loop, and then figure out how high to put the marble, okay? So I'm not going to work through all that. That's just some pretty basic conservation of energy stuff. But I will tell you that I did that problem. I made careful measurements. And I determined, when I made those careful measurements with the meter stick that I have seemed to have lost. Johnny, what'd you do with my meter stick?
It disappeared.
Where did my meter stick go? Oh my gosh. Incorrigible. Okay. So yesterday I did the calculation and figured out exactly how high I would need to put the object in order to get through the loop. You can see my work right here if you really want to. I measured this height, measured that height, calculated the minimum speed here, measured and determined the radius of the loop, and then calculated the height that I had to put the ball in order to get through the loop. The minimum speed required to get through the loop. And that minimum speed came out to be 0.36 meters, so 36 centimeters. So let me find 36 centimeters. Right about there. Right about there. So theoretically, if I let go of this guy, he should get through the loop. Didn't get through the loop. Now, some people might say friction and air resistance would prevent it from, would take, and yes, that's true, but not that much. At low speeds, this is pretty low speed, air resistance is not going to affect the motion of this guy too much. And the friction force is going to be very small, and it's not going to affect it too much. So, in reality, even if I neglected completely friction and air resistance, it still wouldn't make it through the loop. It still wouldn't. Anyone tell me why? It's rolling. Rolling. It's rolling. Do rotating objects have rotational energy?
Yeah.
Absolutely they do, right? Can I get this guy to roll without doing work on it? No, I have to actually, of course this isn't on. Oh, the things I go through for you people at home. If I want to get this guy to roll, to start spinning, I got to do work. I don't have to do work. I can let the mass do work. But I had to do work to lift the mass to that height. But then I can let the mass do work to get this guy to rotate. That guy now has rotational energy, right? Your car would not work without rotational energy. It's literally rotational energy that makes your car go. right? It's the chemical energy that gets converted through a long process to the rotational energy of the crankshaft, which spins your tires. Rotational energy of the tires creates the force on the ground that Newton's third law says the force of the ground on the car gets your car to move forward. It's all rotational. So rotating objects have rotational energy. As this object starts to roll down the slope, the potential energy gets converted to the linear kinetic energy and the rotational kinetic energy. Okay? And so the linear kinetic energy equation is 1/2 mv squared. What do you think the angular or spinning kinetic energy?
1/2 I angular velocity squared.
There you go. Right.
I love it.
Where I is going to be the rotational inertia, and omega is the angular velocity, which, if we know the radius of the rotating object, we can convert to linear velocity. Right? Make sense? You're feeling it? You can't see it if you're at home. There, now you can see it. There we go. This is too much to juggle. Okay. I am recording, right? Yes. So you understand that? Makes sense? So we got to take into account the rotational energy. So let's do that. And when we do that, we will explain what we see here in a different way. So I'm going to roll this disc and this hoop with a bar through the middle of it down this slope. Okay. Same mass, but different distribution of the mass. Same radius, same mass. Okay. Which one gets to the bottom first? Going with the lowest rotational inertia.
I think it's this solid disc.
What dictates the rotational inertia of an object? Remember, for a point mass, it's just mr squared. And for a solid object, you can just consider a bunch of infinitesimally small masses and their radii, right? dm.
Oh, so it would be the disc because they have the smaller radius.
Smaller r values for all of the mass that's in the middle. So yes, the disk has a smaller moment of inertia. What about these two?
The one with the bar has a lower.
This guy has lower rotational inertia. This guy has the most rotational inertia. They're going to essentially feel the same friction force if they're rolling without slipping. They're going to have essentially the same friction force. So the same torque, right? But because they have different rotational inertias, they accelerate with the different angular accelerations. We're actually going to show that today, but we're going to use energy concepts to show it. And it's actually probably, as long as you're good with algebra, a little easier than using Newton's laws. But sure enough, the disc gets, oh, that was nice. The disc that gets to the bottom before the hoop at the bar. The hoop at the bar gets to the bottom before the disc.
What if they started rolling with slipping?
What's that?
If they started rolling with slipping?
Then it's more complicated. We'll talk about that, though. There would be a quest problem where you'll have to determine conditions for when, was this guy, what angle does it need to be at or something like that for when, or the coefficient of friction, what does it need to be so that it actually starts slipping as it's rolling? That'll be a fun one. Okay. So, we can come to that same conclusion, right, as long as we know the rotational inertias. And this is what we learned when we learned Newton's laws last year. You learn Newton's laws, and then you learn that, yeah, it gets pretty complicated, especially when you got a bunch of vectors pointing everywhere, and it's pretty difficult. But then you can approach many of those same problems from an energy standpoint, and as long as you're good with algebra, it becomes a lot easier. Significantly easier for some students. And so let's say I have a disk that's going to roll down without slipping, roll down an incline. That's a pretty good circle. And I want to calculate the speed. What are we given here? We're given the height. So I'll call this, actually let me call it why not. Let me make it. Why? Why not? So we'll call this initial position in the vertical direction. Why not? And we have an object of mass m and radius r. And the example in your notes is a disk, but we can use anything. We'll do a disk. So if it's a disk, the moment of inertia for the disk is the moment of inertia for a cylinder, which is 1/2 mr squared, which we proved. Remember that years ago when we proved that? And then let's say that the problem says determine the speed of, specifically, the center of mass of the disk at the bottom. Now, don't write this down. If we wanted to use Newton's laws for this, we would have the component of mg that points down the ramp, which would be mg times the sine of theta. We would now have a friction force that is necessarily there because it's actually creating the torque that is necessary to have the rotation. So we're going to have minus the friction force, which is going to be the coefficient of static friction. Well, actually, it's not going to be that, sorry. It's going to be minus the friction force. It's not going to be the maximum static friction force, unless it's slipping. Heads up. Minus the static friction force. Do I use this for static friction here? I don't remember. I teach too many different physics classes. Okay.
Go back and forth. I don't think we really can.
Okay, good. Minus the friction force, static friction force, is going to equal the object's mass times its acceleration. And then we can use that to determine the acceleration, and then we can use this height and this angle to determine the this height and this angle to determine the distance here, and then we can use kinematics to figure out the final velocity at the bottom, and that would just be, it's not hard, but it's annoying, right? Maybe not annoying, I don't think it's annoying, but a lot of students do. But you can approach the same problem using energy, and you actually don't even need to know that angle. Because if I use energy, I can just say, well, the initial mechanical energy in this system is equal to the final mechanical energy of the system. My initial mechanical energy of the system is, and putting it all out, I have the initial gravitational potential energy plus the initial kinetic energy plus the initial rotational kinetic energy, so Kr naught. That's going to equal the final gravitational potential energy plus the final kinetic energy plus the final rotational kinetic energy. So this is where, if we're dealing with rotation, we add 2 more terms into our conservation of energy equation, which gets a little hairy. It's not too bad, especially since some of these are going to go away, right? So when you write something like that, and there's many ways of writing the conservation of energy law. I think this is probably the easiest one for this kind of situation. And then sometimes you ask for the change in energy, in which case you just manipulate it so it says final minus initial. Okay? What's going to be 0 on the left side if we release the guy from rest?
Both kinetic energies.
Both kinetic energies are going to be 0. And if we're talking about the speed at the bottom, what's going to be 0 over here? Gravitational potential energy. All right. Well, I have expressions for gravitational potential energy. It's going to be mg times that initial height, y naught. I have an expression for the final kinetic energy, 1/2 times the mass times the center of mass velocity squared. And then I have an equation now for the rotational kinetic energy, 1/2 times the rotational inertia for the disk times the angular velocity for the disk squared. These should be like terms. It should be like terms. I should be able to combine them. I obviously can't as they're written. So let's expand things out. Let's go ahead and put in there the rotational inertia for the disk is equal to 1/2 mass of the disk times its radius squared. And then I can also substitute, instead of omega, I can put what?
Is it V over R?
V over R. Linear speed over R. Remember, that linear speed is the linear speed of a point on the edge of it, but we just showed it earlier today that the linear speed of an object on the edge as it rolls down is the same as the linear speed of the center of mass. So I can put both those guys in there. So I get mg y naught equals 1/2 mv squared plus 1/2. And when I do stuff like this, I don't skip steps. avoid making mistakes, I use liberal use of parentheses. So 1/2 mr squared. And really, because I'm dealing with multiple fractions here, I'm going to put mr squared in the numerator. Over 2 times omega v over r, but that gets squared, so it's going to be times v squared over r squared, where r is literally the radius. So I can put the capital R. It's literally the radius of the disk. And then I get cancellations, right? I got a denominator r squared and a numerator r squared.
And mass.
Oh, and mass comes up. Good. Everyone brought mass to the board. So then next step, I get acceleration due to gravity times the initial height equals 1/2 v squared plus 1/4 v squared, right? So g y naught equals, what's 1/2 plus 1/4? 3/4 v squared. What do we have to find? Speed. So multiply both sides by 4/3, right? And square root it, and I get that the speed at the bottom is going to be the square root of 4 g y naught over 3. And Miss Burke would probably want you to write 2 times the square root of g y naught over 3, and I'd probably do that too.
Gee, why not?
G why not? Why reduce it? G why not? There you go.
Funny stuff.
So that's the speed. Now if, let's say an if here, let's make modifications in blue. Let's say I had a hoop. The hoop moment of inertia is what? mr squared. So if this was a hoop, this 2 wouldn't be there. Right? And if that 2 wasn't there, this would still be a 2. And we would just literally have a v squared here. And so the velocity for the hoop, this is for the disk, and the velocity for the hoop would be the square root of g y naught. Why the hoop is slower. It's going to have a... All right? Yeah.
The disk has an extra third inside.
Yeah. So the disk gets there faster. Sorry. My brain's not working. Now, understand physically what's going on. The reason the disk has a higher velocity is because it has more linear kinetic energy, because it has less rotational kinetic energy. The hoop has more rotational kinetic energy by the time it gets to the bottom, because it took more work to give it that rotation, because it has a higher rotational inertia. What force is doing the work? Friction force. Gravity's causing the friction to happen, but it's the friction force that's doing the work. That's like when you stop your car. You ever wonder, how am I strong enough with my foot to stop my car? You're not doing the work. You're just pushing the brake pads into the discs. And the brake pads are doing the work. Right? So the friction's doing the work, but you have to have gravity there to initiate the process. Cool beans? No. Wrong. You fail.
Freezing beans.
That's gross. Alright, I think, is it? Okay. So you feel that? You feel alright about that? Cool. So can I erase all this? I'm sorry, did anyone say anything? Say something?
So can you write that out one more time?
Sure. Yeah, I'll be on campus.
That's beyond this.
What? Oh, yeah. That's beyond. Far beyond. All right, any questions about all that stuff? Okay, well, maybe I'm going to call it there then. We'll talk about angular momentum tomorrow. I'll let you use the rest of the period to work on the energy part of the quest assignment. Anything that mentions momentum, just ignore for now unless you know how to do angular momentum. But for the rest of the period, just work on the quest assignment. The first part of it will be energy. And if you want me to help you with any of those problems, please ask.